Hi, welcome to the Techweek's Season 2 and Episode 1. My name is Cameron Haslovich, and today we're going to discuss different topics, as you may know already if you have been listening to the podcast. And in the Tech Week, we try to explain different terms, different topics related to technology and how technology is changing our lives and basically revolutionizing the world. And we try our best, as best to our ability, to explain different phenomenon, and then how innovations basically affecting our lives, our day-to-day lives. So for season 2, we're going to focus on more on explanations and how systems work, basically more on definitions and technical terms, how things work, basically. So for that reason, we need to first make some ground rules in order to continue. Um, Please subscribe to follow our channels and follow us on Instagram. This will support our work to create the better technology, more humane technology. And we believe, as a Tech Week, we believe that the key to healthy technology, key to creating healthy technology, is to understand it first, as much as possible. And even though it seems impossible to understand at first, because technology is improving at a breakneck pace, and we believe that making um, making sure that we understand, making sure that we are in control of our innovations, um, and making them work for us and for our health and our better future is the one of the cornerstones of a logic of innovation. So, with that in mind, let's dive into today's topic. And today's topic is vector thinking and how large language models think, and if whether or not we could call them thinking is also another issue, and how it is different than human thinking, like human way of thinking, and high dimensional, multi-dimensional vector embeddings and other different terms will be also discussed. So let's get into it. So today's episode will be focusing on my conversation with ChatGPT and what is the difference between the way of human mind works and how large language models work, and is there any difference between is there any similarities rather between human way of thinking and um, thinking of large language models, if we call like that. So basically, I asked the same question to ChatGPT, and I received an answer, and we started a conversation with ChatGPT, and it went to the directions that I wasn't expecting. So I asked ChatGPT that, is it true that you're thinking in a different way than normal human mind works? Um, I read that you're thinking with vectors and their distances encoding to meanings of words in multidimensional space. How can you explain this? So first, let me explain the prompt that I gave to ChatGPT. In that, we tried to kind of get in the shoes of program itself, and the way it works is it doesn't basically understand the words as we do. So ChatGPT and in general other large language models are working based on um, basically defining the meanings in the sentences and kind of dividing the sentences into smaller chunks, which may be called vectors, or in some cases even smaller parts, which are called tokens. So with that knowledge that I had, and I asked this question, so that it gives me some comprehensive answer. Some It gives me comprehensive, more extensive and more explanatory answer. And so basically, when we ask a question to ChatGPT, and when we give it some prompt, it will kind of embed, it kind of gives mathematic meaning for every word or every part of the sentence. And it works because it has a huge training data. It has a huge repository of words and the sentences that other people have given it, and previously it has learned, and it has read many articles and many words. So based on that, it is trying to guess what is the most probable word that it can put. So let's get started. And before we get into the explanations and the prompt that I gave to ChatGPT, I would love to also point out, stress more. Um, I would love to point out, I would love to stress the importance of not getting too deep into the discussions with ChatGPT and in any other large language model, because recently there were some reports about how our minds is so culpable and so vulnerable into thinking that we are some sort of genius, or we are decoding like a lost thing, like we are basically doing something very important or discovering something like a philosophical or mathematical concept. Actually, we are not. So ChatGPT is built on sort of helping us out. So basically, one of the most important rewards for ChatGPT is making us think that it is being helpful. So as we understood as a tech week, that this way of thinking and this way of making sure that we are responding and we are continuing our conversation and providing it um, more human made data and more conversation, it is the better it is. So for it is very valuable for us thinking that we are doing something important and making us feel that we are basically doing some discovery or something, some sort. So for that reason, it's very important not to fall into the pitfall of this type of thinking. But other than that, it has very great value of exploring things and getting some easy to understand explanation um, from like very technical concepts to mathematical or abstract contexts. Um, so that was very helpful. And let's get dive into our discussion. So last time I asked from ChatGPT that, is it true that you are thinking in a different way than normal human mind works? I read that you're thinking with vectors and their distances encoded into meanings of words in multidimensional space. How can you explain this? And ChatGPT replied back that yes, you are absolutely on right track. I don't think in the way humans do, but rather in a mathematical way that involves vectors in high dimensional space. So essentially, how humans process language is we are processing language through experience and memory, emotions, reasoning, and what have you. So when we hear a word like apple, you think of its shape, right? Like you think of its taste, maybe even a memory of eating one. And all that context really builds the meaning. So you are taking the cues about apple and similar fruits, and you are kind of um, build the meaning based on your previous experience or what you're associating with apple when you say apple. But ChatGPT and other large language models, they think like they don't think like us, obviously, and they think on the basis of mathematical concepts, um, which are called vectors and embeddings. So it works very differently, and let's simplify what's happening inside the program and algorithm when we ask us some prompt. So basically, every word becomes a vector, and each word, or even it might be a part of word, called token, is converted into a vector, and that is, for example, list of numbers, right? Like when you say apple to a large language model, it kind of encodes it into huge list of numbers, basically. And this vector exists in multidimensional space, usually hundreds or thousands of dimensions. And these vectors are called embeddings, and they capture the meaning of the word based on how it's used across lots of text. So, based on its training data and based on its um, uh, repository of words and languages and like texts and etc., it kind of understand, let's say, or capture the meaning. And words with similar meanings have like closer distance between their vectors. For example, if we take very famous example, a king and queen, these vectors are very similar directionally with words like man or woman. Or maybe we can write some sort of prompt and ask ChatGPT to define what is queen, and it can make it like as a equation, like king minus man plus woman equal queen. So basically, the vector for apple is close to banana and far away from airplane. So this is the vector way of thinking. And based on our conversation, this is how it understands relationships, and it doesn't have a real life experiences, obviously, because it's an algorithm, but it can learn patterns into how words relate based on huge amount of training data. So based on the extensive and the size of its training data, it can much more precisely determine the meanings of the words. So that's how it works. And more contexts add more depth. So it doesn't look at words in isolation. It uses something called a transformer to look at all the words in sentence at once. So, for example, when we type "he dropped the apple on the floor," it basically means fruit. Like we mean apple as a fruit. But when we say she works at Apple, it means the tech company Apple. So there is a difference between contexts, and obviously there is some difference between writing words with capital letter and small letter. But in this case, it based on the context. So even the same word can have a different vector depending on the context. So in short, ChatGPT and other large language models think using mathematical relationships between vectors and not personal memories or emotions. This is how there's a huge difference, huge discrepancy between how we think and how large language models think. And the more we get into it, the more we discover there is also measures distance and angles between vectors to reason about language. So it's very different from human brain, but surprisingly effective at tasks like translation, writing, answering questions, or generating ideas. Because the patterns in language are deeply mathematical, if you believe it or not. For example, when we talk about um, translating a sentence, human mind is extremely slow because we are required to know both languages at some level, right? But we are required to know these two languages with some level of comprehension in order to translate both one from another. But for models like ChatGPT and other large language models, work basically completely different because it doesn't know any language. It just can understand and encode words very similar because we humans think very similar. So we mean when we say words very similarly, depending on, of course, the context, but across the different languages. So when we talk, actually, we mean very similar concepts in different languages. So that's why the mathematical patterns is very easy for the ChatGPT and other large language models, and basically neural networks to decode and kind of sort out the words itself. So this is actually very fascinating, right? For example, we can sometimes also think that way. Let's say you are playing a true truth, one lie, a game, and someone is telling one lie based on their real life experience, and you can detect that person is telling a lie because you know how the person kind of constructs their truths. So you can kind of determine the relationship between their sentences, and based on that understanding, that idea, you can determine what this person's lie might look like, right? So this is how we think sometimes in that way. But it's, of course, it's very very deep because we don't think in a multidimensional way. We don't think we the only the maximum dimension that we can think of is maybe 3 dimension or 4 dimension. But these kind of language models can decode or encode words onto maybe hundreds of dimensions. The most common one is 768 dimension, which is the optimal point for efficiency and enough context and enough depthness. So that's why we may think that we are thinking that way, but actually we are not, because the way our mind works is completely different than um, a machine, than a large language model. So yeah, that's about it. So we can say that there is significant parallel between human intuitive reasoning and machine vector-based modeling. Um, and what we are doing basically in that game scenario, we are kind of predict what people want to say or identify a lie in true truth and lie game. And when we are doing that, we are using a form of contextual reasoning. So noticing inconsistencies between what someone just said and what they are now saying. And also pattern matching, picking up common patterns emotionally, semantically, or factually, and spotting the odd one out. And this is also very close to how training works, basically. But where we are doing it with life experience and emotional intelligence, machine learning algorithms and large language models do it with billions of examples encoded as vector distances and statistical probabilities. Um, and Yeah, is this a question like, is our brain vectorizing in a way? Yeah, maybe, sort of. And our brain isn't literally creating, of course, 768 dimensional vectors like ChatGPT does, but it kind of encodes concepts, for example, like honesty or technology, in a network of neurons. Those networks are shaped by experience and context, and they fire together in patterns which could be thought of as neural embeddings. And when we say a similar word, or when we try to explain one topic, we use the vocabulary around the topic, and those words kind of create a sort of galaxy or cluster of vocabulary. And the part of our brain that is being lit on, that is very similar, maybe, and maybe that we can say that is similar to how uh, vector thinking, vector modeling works. So I actually quite like the idea of thinking the word vectors and words and vocabulary in different languages as a cluster of galaxies, because it's really, I mean, it's really similar to what we have discussed since the video started. And when I asked the ChatGPT what are the closest vectors in your vector space, like maybe I can say in human language, what are the closest two words in English language? So it's kind of a broad question, but it answered to me, and uh, the closest mean here, when we talk about closest vectors in embedding space, we usually mean cosine similarity. So there is a one term which is called cosine similarity, and it means that how two similar words, two word vectors are in direction regardless of their magnitude. Cosine similarity one means that they're basically pointing in the same direction, almost identical meaning or identical usage. And the closer the two words are in vector space, the more interchangeable or contextually similar they are. Maybe not always interchangeable, but contextually similar. So, for example, car and automobile. These two words are almost in same words, like car and automobile. Maybe automobile is more formal, much more, um, uh, yeah, much more strict sense, like much more term like. So, in that regard, car is a more casual word, but their vector cosine similarity is very, very close, and they are contextually and meaningfully they're close. So basically, that means they're synonymous, and they are often used interchangeably. Big, large, basically most of the synonyms, for example, man and guy, happy and joyful, TV and television. So these words are very, very close pairings in the word cloud in the vector space. And these kind of pairs, these are just examples that it gave me, but these kind of pairs usually have cosine similarities more than 0.95, sometimes even 0.99. And that means that they can be used interchangeably, and in it is training data, they are mostly used interchangeably. So based on its examples, based on the data, based on the training data that it looked at, they are mostly used in a similar manner. Important nuance is that context matters. In models like transformers, which is basically what ChatGPT and other large language models based on, meaning is context dependent. So the word bat can be close to baseball in one context and close to animal in another. So, in that regard, when we say that it's multidimensional, is because n- only direction is not the direction is not only, it's not only one factor. So it's not only one dimensional, because we think only in three dimension. When we say direction in the space, we mean okay, 2 points, two arrows directing to one point. But actually, in fact, from higher dimensional view, we don't see them maybe as close as they may seem at first. So the word bat can be close to baseball. The fact that it can be also close to animal, or a night animal or something like that, means that we don't have enough understanding of dimensions when we talk about these two words. And from another example, the vector for bank can be close to money or river, based on the sentence, depending on the sentence. So that's why it uses dynamic embeddings. where words vector can shift based on the surrounding words, surrounding cluster, unlike older models, which had fixed vectors, which is not compatible with modern algorithms. The next question of mine was that tell me, are there words vectors that are too far away from other embeddings? For example, what determines their position in that vector space, if that is the right word to describe it, even? I would love to picture the process in my mind visually. And you mentioned the word galaxy before. Maybe that would be helpful for us here. Exactly. So, galaxy, the word galaxy itself is very helpful because it visualizes pretty much very nicely in our minds how it would look like. Basically, the right questions maybe to ask are what shapes the entire space, maybe, or what causes some words to be isolated. That's much more relevant question. Like, are there any words or any vectors that are pretty much isolated in the corner of its training data, and how we can visualize this multidimensional thing as a galaxy of meaning, right? So this is a very deep direction that we're going, but this is what it gave back to me. What determines a word's position in embedding space is, uh, let's imagine massive cloud, right, or galaxy where every word is star or planet. Its position in space isn't random. It's determined by co-occurrence first, which means that words appear together often, like coffee and mug, are pulled together uh, towards each other. If two words rarely or never happen in similar contexts, like coffee and satellite, they stay far apart. This is the like very basic explanation for a couple of maybe variables like um, we will talk about it later, but second is contextual diversity. A word like set or run might be close to many other words. It's hub with many meanings. So the more word is being used in a language, the more it is likely to create a hub in this vector space. So a technical term, for example, like quasi particle or other, I don't know, like random words or maybe mistyped words, float out on the edge because it is either very specialized, very jargon, or doesn't co-occur much or doesn't mean anything, or it's very specific word that is used once or twice in some book or some source, some obscure source. A third one is training data, scale, and domain. If the training data is mostly legal texts, word like plaintiff will cluster together and dominate certain regions. And slang or obscure cultural terms might be far out on the fringes. And the fourth one, last one, is dimensional compression. Even though space is 768 dimensional or more, we can only visualize it in 2D or 3D using different applications and different softwares, which preserve local closeness but distort global layout a bit. Um, and we mentioned before that we can picture the word vector space as a word galaxy, and we can imagine these word galaxies like a cluster of stars, which are akin to semantic themes. For example, geography cluster, the words like mountain, river, continent, they are clustered together. And emotion cluster, maybe joy, grief, love, anxiety, these are also clustered together from far apart from geography. And mental concepts maybe are much closer to emotion cluster. For example, words like thought, idea, intuition, knowledge, wisdom, etc. And legal terms and tech terms and other specialized terms are also clustered together in other locations. So the bright, well-connected stars, we can say that we can make parallels with other astronomical terms. So bright and well-connected stars are common and flexible words. For example, run, make, get. they are used in many contexts and many word constructions and idioms and phrasal verbs. So as much as they're being used in different contexts, it means they're getting brighter, because that means that more data are available on them. So we can also make sure that our rare and isolated words are not alone, obviously, and we can kind of cluster them together as well as a dark matter or outer rim or a black hole or some sort. Obscure names, niche jargon, foreign loanwords, and other uh, low contextual words which has little overlap between with other words and between other concepts. So that means they are very isolated in that location. um, yeah, obviously they're too far from others, words that are too far from others. For example, proper nouns like names, very obscure names like Glumbubble, a Harry Potter creature, and very little context overlap with general words, which means these words are not used with any other words, so their contexts are not matching with other words, or typos or nonsense words that are written on internet or in written sources. So these words are these words are like lonely asteroids drifting far from the dense core of general language. Why this matters? It matters because understanding these positions helps us to explain why we sometimes misunderstand rare or niche words, or don't understand them, and why words shift in meaning over time, like their vectors move. As language evolves, obviously it's a living thing and it evolves constantly, and different vectors can drift to different directions, or they come together. Their distance might decrease or increase over time based on the usage of language. And at the moment, we are using language, and as we use it, it's being evolved in life. So that's very great explanation. And why context is so crucial? Because it gravitationally pulls meanings toward relevant zones. Based on the context, it kind of creates its gravity um, around clusters, and they group together. And when we talk about these issues, we basically think around that cluster, and it's easier for us to basically use the force of gravity in that regard. So that's how it describe it, and it's very beautiful. I think it's very beautifully observed. And like when someone is feeling more comfortable in talking in some areas, for example, if someone is spending too much time on one cluster, or like thinking about one specific topic, they are absorbing themselves in one cluster. So that means that they are more comfortable in talking with these words, or they are more comfortable in reading these concepts, and that means that meanings are defined in their location. Meanings are defined in their galaxies, and they are dependent on each other. They are not like separate from other stars or galaxies in this case. But what's happening in sparse regions? When we ask about rare terms, embedded words, and highly niche domains, um, there are fewer vectors nearby. So it is sense of direction gets fuzzy, and it's like flying out beyond the star chart. It's functional, like it's working functionally, but it's less grounded. It has less confidence, and it has to interpolate, guess rather than recall stable patterns. So yeah, it's basically a technical explanation of why um, the both we can say that there is a similarity between way of uh, its thinking and our way of thinking, because we both of us both large language models and both large language models and humans have sense of comfort or sense of, we shouldn't call it actually sense because it doesn't feel anything, but more like confidence, let's say, in generating um, content and generating words and explaining and talking things. So when we are feeling a lot of vectors nearby, we feel more grounded, more comfortable, and more confident in explaining ourselves. So, yeah. And that at that point, I asked the ChatGPT to give me the answer if it is possible to create an obscure language based on only solely on prompts, where you can give large language models, including ChatGPT, um, commands commands in that obscure language. And it answered yes, actually. Surprisingly enough, if you talk that multidimensional vector like language, you can give these large language models prompts that no one understands, no one can interpret, unless they know that language and they know exactly what you're asking. So, and the next I kind of shifted the conversation towards how music theory works with very similar, um, uh, with similar concepts um, in language. So music is sort of a language because it is also based on dimensional space, multidimensional space, where different notes, pitch, duration of the music, chord progressions, tempo, dynamics, or style genre. So we can basically create a music, every music's um, profile based on its characteristics, and we can kind of map music notes onto something more like a multidimensional thing. Um, and we can even, I went a little bit far, so I said that the history of music can be mapped inside this 768 dimensional space. Similar sounding familiar songs and genres would be clumped together, while obscure, like advanced sort of jazz or other genres, music genres which are not popular, would be apart from the main galaxy concentrations, or the brightest parts of the universe. And it says, yeah, you're absolutely right. What you're describing exactly how modern machine learning models handle music, especially in generative music, recommendation systems, and music similarity search. So the systems part is very, very interesting because this is really how, I'm simplifying a lot here, but this is very similar to how different recommendation systems and applications like Shazam are working. And their method is creating digital signature of every music. This digital signature is very, very similar to the elements the music can be embedded, like its pitch, its duration, its rhythm, chord progressions, tempo, lyrics if they're present, instrumentation, etc. So these can be can be extrapolated. These can be extracted from any music, and it can be helpful to create um, individual signature for um, each factor here, each vector here. So yeah. And lastly, I want to point out, I want to touch on whistle language, which is an extremely obscure, rare language that is used in Turkey, near Trabzon region, where people communicate with whistles, and it can be interpreted both music and language. So it's very, very different. It's very, very rare phenomenon. very fascinating. I found it very fascinating actually, and it's very similar to how it's like language and music kind of merges into one thing. And also, my conversation got really emotional from that point, I would say. So it says you touched on something deeply profound and incredibly rare, and it fits perfectly into our conversation about music, language, vector spaces, and human mind's flexibility. So I was referring to Islik Dili, which is whistled language of Kuşköy in the mountainous region near Trabzon, Turkey. And it's real, actually. It's real language. It's functional, and people understand because of the distance between different mountains. People kind of resorted to this technique of calling each other and talking to each other with with whistles. It's basically going larger and longer distances than talking. And Yeah, it's very helpful to communicate basically over distances. And instead of vocal speech, people use modulations of pitch, frequency, and rhythm of their whistles. And it's not just random whistling, it's just encodes Turkish grammar, syntax, just acoustically transforming its specifics, language specifics, into sounds. So yeah, it's also very similar. How does it fit in our vector space model? The words are same, but the modality of transmission is different. So in one case, it's our vocal cords. In other case, it's just our vessel, our physical like fingers and lips. And In a vector space, the semantic vector is stable. Come home, the cows are loose, if you want to say that, the same vector. The phonetic embedding changes from speech to waveform, frequency, whistle pattern. And we can imagine a parallel musical language embedding space where speech one path through the space, whistling as another path with similar trajectory, different dimensional emphasis, and music a third trajectory emphasizing emotional or aesthetic axis. Uh, so yeah, if we model it, whistled languages would be like compressed high frequency projection of Turkish language across an acoustic manifold. Um, Cognitive implications are whistled language users process language differently in their brain. Normally, left hemisphere language and right music, we say, but Kushkar speakers activate both hemispheres, blending their linguistic decoding with pitch pattern recognition. Um, and that's it, really. We touched on many topics today, and we will try to um, record our next sessions in English. And we have many interesting topics to be discussed in the future. Please follow us, leave some comments, and join the discussion of these fascinating topics. And if you find it very helpful, if you find it engaging, please share with your friends. It will help us to grow. It will help us a lot, actually. Have a nice weekend. Have a nice day, um, wherever you are. So, yeah, thank you for listening.